Oh, hi. I didn't see you standing there. That old gag. All right. Anyway, um, so this today we're going to talk a little bit about combustion and mechanisms. But before we do, this is the part of the semester. Excuse me. I have to take a drink. I have to. I'm sick. If you can't tell, or if you've never heard any of the previous four, this is not what I usually sound like. But before we do, phone. Before we do, this is about the time where people have had the first exam already, because by the time you get into combustions and mechanisms, you're usually, if people do the typical 3 exam in a final format, which I do, then you've had your first exam, and what I tell my students is usually fall into one of 3 categories. You're happy with your grade, whatever that is. Some people they just want a C so they can get on with their lives. I can't tell you not to have that attitude. You can. Might catch up to you though by the time you hit a junior. But the other people, they track, and I've seen it, they track every point, and they know exactly, 90% to get an A, or this is how many points they have to lose. They track those points like a doomsday clock. That's really not a great attitude either, but whatever drives you, I guess. But yeah, if you got the grade you want, you're doing this fine, then keep doing whatever you're doing, I guess. A lot of people, they passed their first exam, but they didn't. They thought they could have got better. In your case, especially with my students, big picture wise, those 100 points, because if your exam's typical 100-point exam, are only 100 out of, I don't know, somewhere between 800 and 900 is what mine do. Some classes use 1,000-point grading scheme. So if you look at all the points you've earned through all of your assignments, any quizzes or homeworks, lab scores, if you have a combined lab class like I do at my school, then yeah, big picture wise, you probably are still passing. And just for a typical semester, you're 15, 16 weeks, you have time now, if you want your scores to go up a little bit, to figure out what you did wrong. And the important thing is students don't always get the first few weeks. Sometimes it's like scheduling issues. Like, yeah, the semester just started and I didn't quite get everything settled like it was supposed to. That's easily fixed. But as far as the study time goes, I would say, are you studying? Your study schedule where it needs to be? Typically, most people say, 2 hours per credit hour is the normal study time you should take for a typical college class. Most people who take a chem class would say that's definitely the minimum. Are you doing that? And if you're doing it, how are you doing it? Some people will say, well, I'm doing all of these practice problems that, teacher gave. That's good. But at the same time, how are you doing the problems? Are you just kind of doing them and seeing if you got in the key and then looking at the solution and say, okay, yeah, that's a solution. If you are, then you got to change things a bit, because, if you got the problem right, then good, you're on track to knowing it. But one way to check to make sure you really got it right, or you really know what you're doing, is always tell, students to play tutor. Either if you're in a study group, take turns being tutor to one another, kind of like I'm doing here. Or what I did back in the day when I was in, I forget the name of the undergrad library at Chapel Hill now. House? Could be. Yeah, House undergrad. Or Davis, the really big one. I just find a corner and I would just mumble to myself. I would verbally pretend I was telling somebody, okay, to convert this to this, you got to divide by this, and yada, 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 yada. Because if you can explain it to somebody, then that's a good chance that you know it. It's like the old adage says, if you can teach it, you know it. Also, too, back in the 90s when I was mumbling to myself in the corner, that was a lot weirder than it was now. I just couldn't just put a Bluetooth headset in and pretend, oh, he's talking to somebody. No, he's in the corner mumbling to himself like a crazy person. Or not. Most people didn't care. It's Chapel Hill, right? So, I mean, getting the problems right, that's an extra way to make sure that you really understand what you're doing. If you find yourself trying to practice problems and you're getting them wrong, you just keep getting over and over and over again, and you're still getting them wrong, well, you can do 100 dimensional analysis problems, 100 stoichiometry problems, and it may never click if you're just if you don't have a clue what you're doing. So if you get a problem wrong, before you try another one, just look at it and say, okay, why am I getting it wrong? You can look at other examples, look at similar examples, and there are plenty of places where you can do that these days. You go to YouTube, you type any subject, you type in gram to mole, you're going to get a bunch of other examples. So you look at those examples, compare it to the example you're given. The setup's usually really similar, and work out, because again, if you do 100 problems and don't know what you're doing, you're kind of wasting your time. If you do 2 or 3 and you really try to figure out what you're doing, then it'll probably click. Then you do the other 4 or 5, however many you want to do, just to check yourself. 4 or 5 may be too many. I just pulled a number out of my head. But yeah, that's the idea. I mean, the why is the important part, which with grading, if you got something wrong, make sure you know why you got it wrong. Right? I see this in my class a lot too. I'll ask questions on quizzes. Students will miss it. On the test, the exact same question. Well, not the exact same type of question. Gram to mole questions. How many moles are in this many grams of this thing? I changed the thing, but it's the same question, right? And they miss both. So the whole idea of a quiz is to quiz yourself, and if you get it wrong, that's okay. It's okay to lose a couple points on a quiz. Again, you can be 10% wrong usually. If you have a 10-point scale, you can be 10% wrong during the semester and still come out with an A. 20%, you get a B. You can be wrong 30% of the time in most college classes and still get a C. If you're wrong more than 30% of the time, though, you might want to stick around again. But yeah, the whole idea, don't focus so much on the points. Focus on, okay, did I get it right? No, why didn't I get it right? And if you figure that out, the next time you see that question on a test or a final or something very similar to that material, which is big in General 1, then you'll get those. Well, you don't get them back, but it'll save you more points down the road. All right. And finally, if you just bomb the test, again, for most classes this early in the semester, again, everything I just said to the second group, that still applies to you. Figure out what you're doing wrong, and just be honest with yourself. Am I studying enough? Am I studying the right way? And as far as getting help, what I always like to remind people is there's plenty of places to get help. For most classes, the teacher's usually the first place, especially at a 2-year school. I mean, nothing against the university guys, but at a 2-year school, our job is just to teach. We don't do anything else. For most of us, some 2-year schools do research. We don't. So yeah, like I always tell my students, it's my job to help you understand this stuff, not make you. I can't make you do anything. And I like my job. I'm doing this this isn't my office. God, I wish it was. It's a nice big room. My office is a little bitty. It's my job to teach you this stuff, and I like my job, and so I like it when students figure this stuff out. So I tell students, don't think your teacher is Gordon Ramsay. Unless your teacher is Gordon Ramsay, and that's just weird. Why is he teaching chemistry? But don't forget all the other resources. Don't forget your instructor, and if you're my students, don't forget me. No, I didn't finish the analogy. I like to don't think of me as Gordon Ramsay yelling at you at the kitchen. I'm like that. the nice father figure helping you make the cookies and say, hey, look, dip the in here and stick it in the oven. Hitting this fun little kid who may be 10 years older than me, because the average age at a community college is 30. But anyway, that's my 2 cents regarding exams. If you're happy with your grade, keep it up. If you're not, you got plenty of time to turn it around. Usually another thing I tell my students, I'm basically telling you everything I told my students, if you got a bad grade, show them that it's a fluke. And there's plenty of time to turn that around. And if you're wondering why my throat is shot, is because I spent the last 2 days telling this to about 24 students. But anyway, you're welcome. But moving on, that's the word. So starting off with General 1, we're going to talk a little bit about combustion reactions, which is usually the first type of reaction that you're taught after a little intro to, just chemical equations in general and balancing. Usually we lead off with combustion reactions, and later on we talk about some things in solution. So with combustion reactions, the one thing to remember about combustion reactions, unlike the ones that we've talked about later in the course, is that combustion reactions are depend on basically depend on what elements are in the combusting substance. And the way combustion reactions work is combustion reactions are identified as the reaction of something plus oxygen to give you some products. So when you talk about combustion, it's always something plus oxygen. And remember, oxygen is diatomic. It's O2. Never put just O. So the products are determined by what's being combusted. So if your combusting substance contains carbon, then one of your products will be CO2. If your combusting substance contains hydrogen, one of your products will be water. And carbon and hydrogen, remember, are non-metals. If it contains any other non-metal, it'll form one, maybe more, oxides of that non-metal. Because basically what's happening is, and we'll see this when I do a couple of examples, is that the elements are reacting with oxygen to form their main oxide. And a lot of times in general Gen Chem, you don't have to learn specific oxides, because non-metals will combine in different ways. But the oxides of carbon and hydrogen, those are so common that usually those two are highlighted specifically, because they happen almost anytime you burn something. Burning is combustion. There's carbon and hydrogen in there, and the carbon is going to primarily form carbon dioxide, and the hydrogen is going to primarily form water. Some people will point out carbon monoxide, but if the combustion is what we call complete or ideal combustion, then it's going to all convert to CO2, which is why people with a gas furnace, they're told to watch out for faulty furnaces, because you get incomplete combustion and you're going to form carbon monoxide instead of CO2. But that's an aside. So basically these elements are combining with oxygen to form some type of oxide. And we're talking about the non-metals so far. The same thing happens with metals. A metal can combine with oxygen to form its main oxide. Squeeze it on there. So, for example, whoops, oh, I started at the bottom, not the top. Oh, that's all right. Let's say let's take as an example the combustion of this carbon hydrogen compound. To blow that up a bit. Here. Whatever that compound is, it's actually later on you'll find out it's probably more than one type of compound because we're looking at an organic compound, carbon based, which you'll see organic examples a lot. Usually in Gen Chem we stray away from organic examples unless you're an organic chemist. Then you like using organic examples because organic chemists are weird. But sorry, organic chemist. I'm not sorry for anything I said. I'm just sorry you're an organic chemist. I'm kidding again. But anyway, back to the problem. I'm sick. So if you want to write an equation showing the combustion of this compound, then remember the way combustion works, that guy is reacting with O2. So remember, anytime you see carbon in the combusting substance, one of your combustion products is predicted to be carbon dioxide. And it doesn't matter how many carbons you see in the formula, it's gonna be carbon dioxide. Yeah, and this throws people off because, well, there's 6 here and there's 1 there. You're jumping ahead. You're thinking about balancing. And you can't balance an equation until you have the entire equation. So put that little thought aside for a minute. So again, you see carbon, put CO2. That's all you put. Say it with me. Carbon, right, CO2. You probably had the same reaction my son did when he used to watch Dora the Explorer. But hydrogen, you said nothing. You're just looking at me. Is going to go to form water. Yeah, no matter how many hydrogens you see, you know, H equals water. All right. So there's nothing else in this formula. So there shouldn't be any other products, or we wouldn't predict any other products. So now we go back and look at the fact that it's not balanced. So just say a little bit about balancing. When I balance, the tips I give students is, one is just to take it one atom at a time. And usually what I do is I just start at the first element and just work my way across. The only real exception to that is if you see an element that's in one or more reactant or one or more product, like oxygen is, or really any combustion problem, you're going to have oxygen all over the place. You'd save that one for last. Although if I go left or right, I'm going to anyway. So yeah, just take it one element at a time. You got 6 carbons here. You got 1 here. Now we'll fix that carbon problem and put a 6 in front of CO2. Moving on to hydrogen. You got 12 here, 2 here. Put a 6 in front of water. Now we look at oxygen. So ideally, we want to just put a coefficient here, because if we mess with any other coefficients, that's going to screw up carbon and hydrogen. What am I doing? I think I got to say. So it's always something with this tablet. All right. Must be moving my arm. Oh, I got to go back to this. Back to the pen. All right, so where was I? So we got 6 carbons here, or 6 carbons, 12 oxygens here, 6 here. That gives you a total of 18 oxygens. 8. So if we just multiply 2 times 9, That'll give us 18 here. And we can go back and check. We got 6 carbons on both sides, 12 hydrogens, total of 18 oxygens. It looks like we're balanced. Oops, forgot to turn my Bluetooth off. Who is calling? Oh, anyway. All right. So it's yeah, that's we have a balanced equation for the combustion of C6H12, whatever that thing is. All right. So moving on. Is anything else turned on? I think I got everything shut off now. It's the 5th show. I got to remember. Plus, I'm sick. I'm sick. That's my excuse for anything else goes wrong today. That's my excuse. I'm sick. All right. So let's look at another example. Let's look at aluminum. Oops, actually, it's not that one. It's not aluminum oxide. I set it up wrong. It's going to be aluminum carbide. Here we go. Thanks. All right. So, again, we start with the given substance. Now that I've changed it to the correct substance. Oops. Try to pretend we've been using this pen for 5 weeks now. We should know how to use it. So, and remember, whatever substance is given, that's one of your reactants. So the other reactant is going to be O2, because that's how we define combustion reactions. It's something reacting with O2. Parkinson's looking. Now it's even worse. That's okay. So to predict our products, again, we just look at the elements in the combusting compound. So aluminum is a metal, so it should react with O2 to form aluminum oxide. And if the element's a constant charge element, like aluminum is usually +3 because it's in group 3 or 3A, then you should be able to use the crossover method to come up with the right ratio. Hey, there's carbon. So anytime you see carbon, no matter how many you see, it should combust to form CO2. So now we have our complete equation. We can go back and balance. So let's see, 4 here, 2 here, put a 2 in front of aluminum or aluminum oxide. 3 carbons, 1 here. Give myself enough room. We'll squeeze a 3 in front of CO2. And finally, to balance our oxygens, we got a total of 2 on the left. We got 2 times 3 is 6. 6. 3 times 2 is 6. And that gives us a total of 12. So if we put a 6 in front of oxygen, that should balance our oxygen. So yeah, 4, 4, 3, 3, 6, 6. Or not, 12, 12 rather. And yeah, looks like it's balanced. All right, finally, we'll look at one more. And we'll look at, again, another organic compound. Again, they're really common examples. Let's see where I'm at. But we'll look at this thing, whatever it is. And again, if it's 8 carbons, it's probably many different things. You guys will learn that later in the semester. This thing called isomers. Different compounds that have the same molecular formula. But that's a ways away. But anyway. So that thing is going to combust, which means it's going to react with O2. Looking at our products. Carbon, again, no matter how many carbons, CO2. Right. You got hydrogen, which means you're going to form water. Now, if oxygen's in the combusting substance, this is sort of kind of an exception to what I said earlier about, non-metals forming non-metal oxides, because oxygen is not going to combine with oxygen to form oxygen oxide. That's really just oxygen, right? So really what happens is that oxygen gets mixed in with the oxygen to form the other combustion products. So again, if you want to think of it as an exception, that's fine. You don't get any kind of special product when oxygen's in the formula. Everything else will go to form its main oxide. All right, so at this point we're done. Since oxygen is not going to give us the third product, we've got all of our combustion products, or what we predict would be our combustion products if everything went according to plan. So now we go back in balance. So 8 carbons, put 8 here. 18 hydrogens, put a 9 there. All right, for your oxygens, see on the left we got 16 there, 9 there. It gives us a grand total of 25 oxygens. And again, if we're just going to focus on this coefficient, then you don't want to forget about the oxygen in the other reactant. So really, we just have to, since we want to keep that one at 1 because that'll screw up the other coefficients. So really, if you take away those 2 oxygens, we really have to balance a total of 23 oxygens on the left side. And you can do that. The easiest way to do that is to put 23 halves there. Which, when you get to college level chem, most instructors will say that fractional coefficients are fine. If yours don't, then that's his prerogative. But in my case anyway, I'm okay with a fractional coefficient, because when we look at coefficients, I try anyway to emphasize the fact that, think about those coefficients on the mole scale. Don't think about individual atoms and molecules. And you can have half a mole, just like you can have half a dozen. So for me, fractional coefficients are okay. If you don't want to keep the fraction there, or if you had an instructor before and he just grinded that into your head, or in some cases when you're doing reaction math, the fraction can make things a little weird. You can multiply everything by the denominator, 2 in this case. And that should still give you a balanced equation. So again, for all 3 examples, notice you're basically going through the same steps. You're looking at you're just looking at each element in the combusting substance, and combusting substance, whatever it is, reacting with O2, and you're putting its main oxide on the product side. So you see carbon and hydrogen a lot in these kind of problems. Carbon, no matter how many carbons are in that initial reactant, is going to form carbon dioxide, CO2. 1 carbon, 2 oxygens. No matter how many hydrogen you see in the problem, you got to put water down on the product side. Any other nonmetals like, or any other nonmetals except for oxygen, you would put its nonmetal oxide on the product side. If you have to know any more nonmetal oxides, most classes, it's just carbon and hydrogen, because those are the 2 biggies. But any other nonmetal, it would form its main oxide. Again, oxygen's sort of kind of an exception. You wouldn't form an oxygen oxide because that's just water. And if it forms a metal like aluminum, you would form a metal oxide. So yeah, there's combustion reactions. I need some water because my throat's killing me. You're welcome. You're welcome. Like, you can't Google combustion reactions on YouTube. Google on YouTube. Is that a thing? You can't do a search for Google combustion reactions on YouTube and find 1,000 hits already. I'm really pushing the movement forward, aren't I? My dumb little show. But anyway, moving on to General 2. So with General 2, I thought we'd talk a little bit more about kinetics, because usually in this point in the semester, you're still talking about kinetics. Most is. So I thought a good topic to cover will be to say a little bit about mechanisms. I guess I can keep it here. There we go. And the idea behind a mechanism, which is kind of interesting on some way, how mechanisms often come up by the same time the General 1 guys are learning equations. Because when you're first taught equations, you just say, okay, here's some reactants. They're going to form these products. But, you know, a semester later, you talk a little bit more about the fact that it's not just a straight, hey, reactant to product. There's some things that will often go on in between. And if you want to see all the individual steps that occur in a reaction, that's what a mechanism does. So an example I like to use these days is the reaction between, or the conversion of ozone to elemental oxygen, which some of you may not be old enough to remember, but before global warming was the thing that was going to kill us all. The depletion of the ozone layer was the thing that was going to kill us all. Before that, it was gangster rap. Before that, it was nuclear power. Oh no, before it was the rainforest was going to go away. Then it was nuclear power. And before that, I think it was Nixon. The point is, Gen Xers are jaded for a reason, because we've heard it all. But anyway, going back to this. Sick. Water. So this is a common way people show how ozone converts to oxygen up in the whatever sphere, troposphere. I think that's right. Which again, it's a naturally occurring thing. And it's just the whole ozone thing that you hear about that people were panicked about in the 90s was that we were dumping stuff up into the ozone layer that was screwing up nature's naturally occurring ozone oxygen conversion process. Because we'll see in a minute, oxygen actually converts back to ozone. But yeah, the way the ozone layer protects us from these harmful UV rays is that it absorbs some of that UV energy, which facilitates the reaction or the conversion to O2. But it's not just two oxygen reactions colliding to form 3 oxygen molecules. It's usually shown as a 2-step process. And the first step is an ozone molecule absorbing some UV energy. That energy breaks a bond, which remember you were taught back in General 1. It takes him on to form O2 and an oxygen atom. And that oxygen atom will react with a second ozone molecule to form a couple more O2s. So notice a couple things about this mechanism. First, if you add these two chemical equations together, just like you would math equations in algebra, you know, the oxygens are on opposite sides of each other, so they drop out. Everything else on the left is O3 plus O3 gives you two O3s. 1O2 plus two O2s is three O2s. They add together to give you the overall reaction. So again, this is the overall reaction. Let me do that. And this is actually showing you what goes on in between as you go from those two oxygens to those three, or those two ozones to those three oxygens. It'll work. Not well. Also, too, notice that we're forming oxygen in one step, but then it reacts in a later step. You see that a lot in mechanisms. And that's the thing that we call an intermediate. Intermediate. So an intermediate is, again, produced in one step, but it gets consumed or it reacts in a later step. And those are very common in mechanisms. As you go from step to step, you might form something that you don't see in the overall process because it's basically, if you think about it algebraically, it gets canceled out. It's produced in one, reacts in a later step. It gets basically cancels out during the addition. So that's the basic gist of mechanisms. And one thing that we look at in mechanisms in particular are these things called the rate determining steps, sometimes called the rate limiting step. I like rate determining for reasons that might become apparent in a minute. Determining step. But basically, the rate determining step that has the biggest effect on the reaction, and has such. Well, I'm kind of jumping ahead. I'll go with that now. Its effect is so. There's such a large effect on the overall process that the overall rate law is usually equal to the rate determining steps rate law. Which, more on that in a minute. But the way you identify the rate determining step in a mechanism is that it is the slowest step. And in most cases, what'll happen, for a typical general chem problem is that you're not given any rate data. You're just told, hey, this one's slow, this one's fast. So, for example, looking back at our ozone mechanism, oops, that's actually the overall one. All right. For a typical problem involving rate determining steps, again, you're just told, hey, this one's slow, this one's fast. All right. How does your teacher know that this one's slow and this one's fast? Well, he either looked it up in a book or he just made it up. It doesn't matter. It still works as a problem. So just somebody somewhere, I'm sure, has experimentally determined these two processes, and they know which one's slow, which one's fast. Probably this one is a slow step, but I don't know. I'm just taking a guess. Decomposition is probably faster than this reaction. Or no, actually, that might be the faster. I think I got that flipped. Doesn't matter. In this example, it's the slow step. Who cares what's happening in real life? Don't involve real life in Gen Chem. Let's keep it general. You can deal with real life after you transfer. That may not be entirely true. That was bad of me to say. Forget I said that. I'll edit it out. I'm talking a lot more than I usually am because I'm sick and I really don't care. Have I mentioned I'm sick? Yes, you have, Mark. Shut up. Just show me how to do this problem. But anyway, so if this is the slow step, if the first step is a slow step, then again, by definition, it's going to be the rate determining step. It's predicted to have the biggest effect on the overall rate of the reaction. And the reason is because it's so slow that it's usually so much slower than the other fast step or other fast steps if you got a mechanism of 3 or more steps. That, just by how we measure things, that the overall rate law should match the rate law of this step. And when we first introduced rate laws, we talk about how for the overall reaction, you can't predict the rate law just by looking at the equation. But for a step, that's exactly how you do it. So the rate law should equal some rate constant, ugly K, times the concentration of ozone. And it'll be to the first order because it's a coefficient of 1. Yeah, the reason we can't do that for an overall reaction is because, again, there's some little bitty stuff that we're not seeing in the overall reaction. But by definition, a mechanism shows you the individual steps. So there's no in-between part in a step. That ozone is going to decompose, and there's nothing going on in between. So mathematically, this should be true. It should be first order. And there's some math to it, but I'm going to skip the math because I want to. So experimentally, if this is the mechanism and this is the rate determining step, remember, before you talk about mechanism, usually you talk about ways you can verify the order of reactants. One way is by plotting the reaction over time to see how you can get a straight line. And if it really is first order with respect to ozone, then if you take the natural log of ozone's concentration, plot it over time, you should get a straight line. Or you can also use the initial rate method, which we talk about before mechanisms. Again, it's one of the ways that we experimentally determine a rate law. So again, experimentally, if it's a first order process, if you increase the concentration of that ozone by a factor of 2, for example, then you should see the exact same effect on the rate. If you triple the concentration, the rate should triple. And that's how you see a first order relationship in using the initial rate method. Which I thought about doing that today instead, but again, back on my old Gen Chem Concepts videos, I do have a one for the initial rate method. If you got annotations up on YouTube, if you can see them, I'll pop one up, maybe. Unless I want to put it somewhere else later. But so yeah, if this is how you this is one way to verify a mechanism. If this is actually the rate law, one way you can verify it is to see whether or not the rate determining step matches the rate law of the overall process. And some people will ask, well, what about the fast step? It's not important. It is important, but again, on this time scales that we measure, usually the slow step is so much slower than the fast step that the time it takes for that fast step to occur is negligible. So I use and a lot of people use a traffic analogy. Traffic analogies work well in kinetics. That basically the rate determining step kind of, in a way, bottlenecks the reaction. So for example, let's say you're traveling in interstate. If you live in a metro complex like I do, you're driving from work to back home. And for a lot of folks in the Research Triangle area, we're going to try to drudge it through I-40. So, you know, 5 o'clock rolls around, you jump in your car, you're speeding down the interstate. You want to get back home to Raleigh before you hit the Beltway. But there's a wreck. It's in the other lane. God dang it. But so, yeah, you're pretty much stuck in that bumper to bumper traffic until you get through it. So most of your time spent during your trip home is in that, you know, quagmire around that wreck that was in the other lane. My God, nobody's ever seen a wreck before. Move! Or you can do like I do and just avoid the interstate at all costs, but not everybody can do that. So yeah, no matter how good of a time, how much fun you were having, no matter how good time you were making before you got to the traffic jam or after you got to the traffic jam, if it was a mother of a traffic jam, most of your trip was spent stuck in that step of your trip home. And for, you know, a reaction occurring on the atomic time scale, because these reactions usually happen pretty quickly, a lot faster than it takes for you to get home. The slow step is so much slower that this is just what we see. We see that the slowest step, its rate usually matches the overall rate of the reaction. So, you know, when the first step is the slow step, then it's pretty straightforward. You just, you know, the rate equals a rate constant times the concentrations raised to an order equal to their coefficients, kind of like we see here. The more involved mechanism problems are when the first step is one of the fast steps, or the fast step if you got a two-step mechanism. So let's look at this problem one more time. And now let's just say, for sake of argument, that, or for sake of a good problem, good example, good night, that the second step is the slow step and the first step is the fast step. So again, whatever the slow step is, that's the rate determining step. So as far as identifying the rate determining step, you just look for the one that has the word slow beside it. To figure out the rate law that you'd expect, kind of like we did a minute ago, again, you can figure out the rate law just by looking at the equation. You know, unlike the overall reaction, which requires, you know, things like the initial rate method or plotting. You know, the rate should equal some rate constant times the concentration of each reactant raised to a power of their coefficients. And since both of them have a coefficient of 1, both of them should be first order. But when you have later steps, when the second step or later steps are rate determining, a lot of times you're going to run into a situation where your intermediate is part of the rate law. And you can't have that in your rate law. Intermediates usually aren't part of a rate law because they're not actually part of the overall process. Again, the overall process is ozone going to form oxygen. Whoops, 3. Now you say, okay, the rate law is equal to this. They're going to say, oh, wait, what oxygen? There's no just O, no monatomic oxygen. They probably say monatomic oxygen, no, just O. Where's this O from? I don't see it. So it's usually too confusing. So unless you're doing research that actually needs, where you're actually studying intermediates or some other weird thing, in most cases, you know, the convention is you don't have intermediates as part of your rate law. So we need to get rid of the intermediate. So to do that, you actually have to do a couple of things. First, you have to you have to look at the go back and look at the first reaction, the first step rather. I try to say step when I mean step. Steps are technically reactions, but to avoid any confusion. Speaking of confusion, this pen is confusing me. Eraser. There we go. Pen. All right. Oh, might be the UPS guy again. I got to start scheduling these when the UPS guy ain't coming, or I got to stop ordering so much stuff. So, yeah. So, where was I? I was thinking about the UPS guy now. So anyway, you go back and look at the first step. So if it is the slow step, relatively speaking, if it's slower than, the step that occurs next, what will probably happen is you're going to start to build up product. An example I like to use, speaking of UPS, God, maybe that was that's actually a good segue. The example I actually use involves the summer that I spent the trucks parking at part of town or wherever they need to go. I was one of the guys that worked in the back of the truck, and my job was just to take the stuff, pull it off the truck, and put it on the belt and put it up the hill, the conveyor belt. So what I would do is, what most sorters would do is they would try to pull that wall down as fast as they could. Because if you could get it on the conveyor belt as fast as you could, and you could go faster than the guy sorting, then he would stop. He would make you stop so he could catch up, and you would be able to take a break, because the back of those trucks are hot. At least they were back in 1900. So again, in a chemical reaction, it kind of works the same way. If the first step is faster and it's throwing product at the second step, well, the second step can't tell the first step to stop. I guess that's where the analogy breaks. But if the first step is throwing those products faster, that intermediate faster than the second step can use it, it's going to cause the products to build up. So what you see is eventually you build enough product where the reaction will start to occur in reverse. And this is something we typically talk about, which eventually it'll establish what we call an equilibrium. Gotta learn to hold my pen right. Then I hate problems. There are all sorts of problems. I cannot write the word equilibrium. I mean, I can write it on most days, but I can't now. Go figure. I'm gonna try it one more time, because now it's a matter of principle. Equilibrium. Screw it. Some of you might have kids around. I'm not going to say the F word. Equilibrium. If I remember, I'll show you why this keeps happening, or I think it keeps happening. But it starts to react in reverse. And when you form an equilibrium, we'll learn this in a later chapter. Equilibrium basically means that the forward reaction and the reverse reaction are happening at the same rate. So the forward reaction involves ozone being converted to O2, oxygen, There we go. And the reverse reaction is O2 reacting with that oxygen atom to reform ozone. And this is the part for all you fans of environmental disasters, how we thought we were screwing up the ozone layer. Because this process of ozone breaking down and reforming occurs naturally, but all those CFCs we were pumping up in the atmosphere was screwing up this cycle of ozone being formed and reformed and decomposing and reforming. So the rate law of the Ford reaction will equal, Jesus Christ. That way. There we go. All right, so the rate law is going to equal some rate constant. Here we'll call it KF. Stand for Ford. Times the concentration of ozone. Oh, it's disappearing. The second, in the reverse direction, ugly R. The rate law is going to equal some other rate constant. We'll call it KR for reverse times screw this thing. I'm going to redo it. I'm going to do it on Word. All right. So problem is I got this little button and I keep hitting it. And I think that's why the eraser keeps popping up. It's not happening in Word, so forget this other thing. I thought the other thing would work better. It worked better when I was testing it out. But screw it, I'm going to do Word. Live shows are fun. Have I mentioned that before? All right, anyway. So let's see, let me rewrite. So the rate law of the, actually I'll rewrite the steps. Oh yeah, and then that happens. Yeah. Turn this button off. So the rate law would be equal to the Ford rate law times concentration of ozone. That's the Ford reaction. The reverse reaction will equal O2 and O, because in the reverse direction, O2 and O are the reactants. So what I said before technology collapsed on me was that we're assuming this thing establishes an equilibrium, which means these two rates, whatever that rate is, they're going to equal each other. So we do a little bit of algebraic trickery, or massaging of the data, whatever you want to call it. Do a bit of algebra. And we can basically combine these two into this reaction. And we can tweak it a bit more by rewriting it where the intermediate is by itself. Well, that's O3. So yeah, there's our intermediate. And in our rate determining steps rate law, Rate equals some rate constant. Here we'll call it K2 just so we can keep all our K's straight. Times the concentration of O2 times the concentration of O. Or I'm sorry, it's O3, right? Let me. Like I did. Yeah, O2. Although I had it backwards for same difference, huh? Yeah. All right, it's O3. So yeah, that's the intermediate we're trying to get rid of. Here's an equation that that relates our intermediate to all of this stuff. And notice that both of the substances are part of the actual equation, the overall equation that we're talking about. So if we sub that into here, get rate equal K2 times O3 times Kf over Kr times O3 divided by O2. And we can clean it up a little bit more, or a little bit, period. We'll lump all the K's together. O3 and O3 will give you O3 squared divided by O2. You get O3 times O3, O3 squared. And since we're just working with whatever these numbers are, instead of having a bunch of individual constants, let's just lump them all together into some other constant that we'll just call K. And that'll give us O3 over O2, or you can write it as O negative 1. Which that's why I like the other one, because you do undo and it doesn't take it all the way. Because remember, with rate laws, we usually see zeros, ones, and twos the most, but orders can be anything. You can have a negative order. It doesn't happen a lot, but it can happen. It's happening here. All right. So, yeah, now we have a rate law that we can look at experimentally. Yeah. Again, if we're looking at the overall reaction, I'll write it one more time. Now everything in the rate law is in the overall process. So we can experimentally determine the order of the overall reaction. So again, you can do it experimentally for ozone. For a second order process, you get a linear plot. By plotting the inverse of concentration over time. Or if you use the initial rate method, if you double the concentration of ozone, the rate should quadruple. That's what you usually see with a second order process. If you double the concentration, rate should quadruple. It should be the square. Because again, we're looking at these, that's what a second order is the square of the concentration. And you can do the same thing for an order of -1. If you know how to do a linear plot for -1, usually don't do those in Gen 2. You can do it using the initial rate method, though. I mean, if you can double the concentration of oxygen in your reaction. I know it's a product, but when you get to equilibrium, you'll see how you can do that. And the rate should increase, or actually decrease. Go down by 1/2. Or no, it increased by 1/2. No, that's right. the rate would go up by 0.5, which I guess is really a decrease, but same difference. The point is you can experimentally determine what the rate law is. And if what you're seeing experimentally matches the rate law of your rate determining step, then there's a good case, or there's a good possibility that is the actual mechanism of your overall reaction. And I say there's a good possibility, it's a viable mechanism, because you can come up with different types of mechanisms that have the same intermediate or have similar rate laws. In my book, I can give a couple of examples. But for it to be any kind of possible mechanism, that's what has to be true is that the experimental rate law should match the rate law of the rate determining step. So again, what you're seeing experimentally matches what you're seeing theoretically. Yeah, theoretically, what we see is that the slowest step, that rate law matches the experimental rate law a lot of times. Maybe not every time, but a lot of times. So if that's true, then there's a good chance that's the mechanism for that reaction. If you can come up with a couple different mechanisms that have the same rate law for maybe not the same rate determining step, but you come up with different mechanisms that give you the same rate determining step rate law, well, then that's when you gotta figure out something to determine which one's which. But that's beyond the scope of General 2. That's somebody's master's thesis in a lot of cases. But we're not going to do that. All right, so that wraps up today's issue. Last I checked right before the show, and nobody had any requests. So if you are watching these week to week and you want me to, want me to work something out that I'm not planning, then you go ahead and tell me. I'll either, has it really been an hour? Jesus Christ. It's been an hour. If I have time, then I'll do it in the end like I did last week. Or if it's one that, God forbid, like more than I get a lot of people giving requests. If a lot of people make the same request, I'll say, screw it, I'll do that instead of whatever I planned. But yeah, just let me know in the comment section next week when that the event gets scheduled, which again you can check at my Google Plus page, all the annotations that you saw at the beginning. If you have annotations turned on, if you're watching on a tablet, you're not seeing any of this crap, or you just turn them off, which is fine. That's true too. So that's the end. I don't have any cute jokes or any dumb stuff to do this week because I'm sick. I'm surprised I made it an hour. So that'll be it. If you did take your exam recently, yeah, one down, however many to go. But yeah, we'll see you next time. Bye.